Good evening, friends. Myself Abhishek Bedi, and I will discuss with you a very important topic for UGC CSIR NET JEST GATE and MSc Physics examination. The topic belongs to Quantum Physics 1, and the basic thing I am dealing today is how to represent an operator or observable in quantum physics in matrix form. So this is very important topic generally asked in UGC CSIR, and normally you will find at least one question depending upon it in JEST gate also. And this technique is not only meant to represent in metric forms only, but for time evolution operators, perturbation theory, you can easily solve various length numericals by converting the operators and eigenvectors in matrices form. So ladder operator I'll start with. Ladder operator is of utmost importance in quantum mechanics. All these operators mostly originate from angular momentum operator, and you will find a book, very well written book on this by Noradin Zetli, in which a full-fledged chapter is given to angular momentum. I'll recommend to complete that chapter from this book only. So L square, LZ, ladder operators, all these are basic important things. In most of the books, Sequoia, like you will find LZ and L square represented in matrix form, and proper mathematical steps are there, but generally no major steps are given in most books for ladder operators. So I'll deal with this. Basically, we'll start with some basic information about for any operator having eigenvector psi1 and psi2, such that when operator act on this eigenvector, then same operator, same eigenvector will appear, as well as with some scalar over there. Scalar may be positive or negative, a1 and a2. So if we have only two eigenvectors for a given operator, then how to represent it in a matrix representation? This is very important. So I'll deal with the bracket notation given by Dirac. We know this is bra psi 1 vector, this is ket psi 1 vector. So what you do? So the operator you need to put into matrix form should be written like that, and from right side, from left side, you have to operate a bracket vector or bra vector. So first vector we have psi 1, so psi 1 here and psi 1 here. This is just like matrix form A11. This is first vector from here, first vector from there. And second, this is, we know that it is A12, first vector from here, second from here. And this is, we know that this is A21, second from here, first from here, and this is A22. Very important, very simple thing to write an operator in form of a two eigenvector matrices, 2 cross 2 order matrix. Now I'll define this with an example. Suppose we have with me, this is Stern-Gerlach experiment outcome. You might have started in MSc Quantum Physics 1 first chapter, very first unit, in which we have a SZ operator act on plus. This plus only means positive spin along z axis, and minus means negative spin along z axis. These are spinor eigenvectors, and here this is the eigenvalues for these two operators. In matrix form, we generally know every ket vector represented by a column vector, and every bra vector represented by a row vector. So let's start with it. So Sz first vector, this is plus 1 from left side, first vector from right side, first vector from left side, second from right side, second from right left, first from right, second. This is just like again a11, a12, a21, a22. Very simple. Now Sz when operate on plus, I'll get h cut by 2. This is eigenvalue and same vector. Okay, and I have written this over there just like 1 0 and minus value this. So you can say when this applied on the same plus vector, which is 1 0, I have written, and this is plus and bracket notation I have written. These two are row and column matrix. Everything is very simplified over here. You can easily undergo the matrix product and find out this to be a SZ representation matrix. Very simple. So this kind of mathematical step you will find easily in J.J. Sakurai and Nardin Zetli, and even in Gupta Kumar Sharma Quantum Physics 1. So what happens to the major issue, that is eigenvector, these ladder operators which apply on GM value. So first I'll make you show what GM suggests. J is the angular momentum, total angular momentum, in which we have the resultant of orbital angular momentum S, L, and spin angular momentum S. just like Lm and Sm. Everybody know that m is the eigenvalue of Lz operator and L is the eigenvalue of just azimuthal quantum number L. So if I have L equal to 1 by 2 with me, and we know that then ml value go from range from -1 to 1 by 2 only. So here it should be ml rather. So for L equal to 1 by 2, there are two sets, two eigenvectors. Just like if L is 1 by 2, m may be -1 by 2, L is 1 by 2, m may be m may be plus 1 by 2. So these four very important relationships I have written over here, and this should be, you need to commit to memory. These, at least one of these will be readily used in your UGC CSIR NET JEST gate examination. So LZ, when operate on this, we know that LZ deal with only m values, so m. L square, this is L plus 1 L. This is very important relation you have done in electrodynamics 1 in various derivations about spherical polar coordinates. So L plus means it is a ladder operator which raises the m value by 1. You can see it raised it by m plus 1, it raised it by 1, and at same time the eigenvalue, this comes out to be this. Only for the MSc quantum physics 1 students, quantum physics first part 1 student need to derive these relationships. Otherwise in UGC NET and JEST and gate examination need to understand them only and cram them as soon as possible. So what happened next? So if I want to, what if to write L plus operator in matrix form? How to write? This is very important. This is main challenging thing you find in I think unit 3 of quantum physics 1. So in most of the books they have written directly or some laborious mathematical techniques used over there, but I have simplified it too much. You can see that for L equal to 1 by 2, I have m value 1 by 2 and -1 by 2. You can easily see. So there are only two eigenkets are with me. So if there are only two eigenkets are with me, this means that the matrix will be of 2 cross 2. There is a general formula to find the order matrix, that is 2L plus 1. So just only put the value of L equal to 1 by 2, you get 2. This means the order is 2. So how to write it? You can see first vector here, operator, first vector, this is a11. First vector from here, operator, second vector, this is a12. First vector from here, second vector, this is a21, this is a22. So I am very easily, you can see that when L plus operator act, L plus raises the m1 by 2 by 1, so that it readily raises it is to be 3 by 2. At same time the eigenvalue depending upon the previous formula, you can see there I have applied this direct formula over here. You can see L 1 by 2, this comes out to be here, this I have done all the mathematics. You can see this is not same as this is, so both are orthogonal, product is 0. These two are same, this means that there are some answer will be, so I have addition, solution, I'll get only h cut. And this is again not same 0, these are not same 0. So this relation is in JJ CSIR only written. I have proved this. So you also need to prove that in examination. It might be a 5-mark question in your MSc Quantum 1 examination, or it may be a 1 or 2 mark question gate JEST examination. So major issue, one issue is all in last. For L equal to 1, this is a generally main problem. For L equal to, we know that m is -1 to 1. This is from class 11th we are saying in chemistry classes how azimuthal quantum number L leads to the magnetic quantum number -1, 0 and 1. So there are 3 eigenvectors. So order of the matrix will be 2L plus 1, which comes out to be 2 into 1 plus 1, it comes out to 3. So 3 cross 3 order matrix will be formed. So now you can see that this is first vector, this is the first vector, this is L, this is m value. This is the first vector, this is second vector, this is first vector, this is third vector. So readily you can write this kind of matrix very easily depending upon your practice. You had to do at least 2 to 3 numerical solved on this. These all type of numericals are given in Nord in Zitli. So this is A31, this is A32, this is A33. So all values I have written. Again, directly I can choose some of them to be 0. For example, L minus if apply, it decreases this by -1, this will come out to be -2 types. So this means that if it is 1 minus 1, it comes out to 1 minus 2, both are orthogonal, this comes out to be 0. This is 1 minus 1, this is 1 minus 1. On application of L minus operator, it releases to 1 minus 1. So both are same, they form finite answer, though I have written it there. So this is 1 minus 1, this is 1 0, again 0. 1 0 1, again it reduces by 1, this comes out to -2, so again it is 0. 1 0 1 minus, this I have to find out, this also 0. This is 1 0, I have to write it, I have written over here. So those which can be 0, I have directly make them 0, otherwise only 2 entities I have with me which are non-zeros. So next point is again to use this formulation. This is very important, these two. In previous example I have used L plus, now I am using L minus. So this is very simple things. So I have put over the answer and final देखो, you can see that this is matrix representation. In no book I think this kind of matrix representation have been proved. I have gone through it. So this is a very important lecture for you all. So this was my first part on the UGC NET CSIR preparation for quantum physics. I will put on daily basis some important questions which are regularly asked in the examination. For more videos and queries, you can mail me directly or comment on the video. Thank you.